This conference will
able to
now
use
be recorded.
desktop. Okay, there is an option of hide everyone at the top, so you will not you will able to see your full screen. So GUI, just search the buttons which will expand your screen. Option of hide everyone at the top. Okay,
Get the full screen. Okay, Pratik sir, you can start.
Yes. Okay, fine. Good afternoon, everyone. I am Pratik Kumar Das from Dio Research and Engineering, and as an application engineer, and I'm going to represent about Flownex, its capability, and for which purpose it is used, and how we are going to build power plant models and different types of cycles. So, Flownex actually is a South African software which deals with one-dimensional CFD, and it is a simulation environment for fluid simulation, and systems and subsystem level simulation can be possible in Flownex. And it is solver is based on iterative pressure correction solver. Yes, it is iterative pressure correction solver is there. So it gets a values and hello, am I audible now? Hello.
Yes.
Yes.
Yes, sir. Continue.
Yes.
Okay.
Flownex is that one-dimensional CFD software, and it can solve different type of fluid-related problems. And the solver Flownex used is pressure-based solver. And in this solver, you can see initially it will initialize a gas value, and from that gas value, it continues to solve in a Newton-Raphson's method and predict the solution. And system.
So Flownex allows you to like performance for plant behavior and performance, and you can make the models like if it is very complex model, so you can make very in complexity, reduce the complexity in the for the very large models. After that, its solver is very fast. It means you can design and build the model, and it will take very less time to perform the models. Like its computing is calculations is it is very fast. So, and after that, if you have some want to optimize the plant operation and the maintenance strategy, so you can do by this also. And because this is verified by the Johannesburg University, and its calculations and the equations are give the correct result, so the decisions are very rightful, so you can choose the Flownex. So after that, so its features are like if you want to plot the visualization like graph and some like if you are working in a power plant or designing the power plant, so like you see here, this is the TS cycle diagram, and you can see the various small points like the Rankine cycle, and before the saturation and after saturation superheated steam and other things. So this also you can visualize by plotting the small point also in the Rankine cycle. If you are using the Flownex to on Briton cycle or Rankine cycle in any power plant system. So these are also special features. And if you want to put a large value like some large Excel data sheets, if you have a very large number of inputs, so you can attach by Excel, and automatically it will take all the inputs from its Excel sheet. You don't have to go every component to uh, provide the input. It will take automatically. So that will save your time also, and your calculation part also. And it's like if you see on the screen, its key technology is it can handle incompressible fluid, compressible fluid network, two-phase fluid, and slurry fluids. If you have a slurry mixture like in power plant, ice handling plant, we have ice slurry mixers, so that also we can perform in this analysis. And heat transfer systems also, like if he has LP heaters, SP heaters like we have in power plant, so that heat transfer phenomena or cooling tower phenomena, heat transfer phenomena also can be performed in boiler system also. And it has a various mechanical components. I will show you how means how many components and which type of variety it has. And control systems like in plant we have all the control instrument part, so like PID controllers and other instrumentation part. Also we can connect to our physical model to the instrumentation model. So we can, if we want to command by our control parameters, so that facility also we can use. And apart from this, electrical systems, like if we want to extend our model up to switchyard or generator systems, so that has also some component in that, so that we can also use. So it has a user-friendly techniques. Like if you see on the screen, it has a curve of water hammer. A surge is happening in a water line. If the valve is suddenly closed or open, so closed, so that's why. And so it has a very it can run more than 200 transient scenarios at a single time, and automatically it is reporting to the Excel sheet. If you are performing any analysis and you have a large system like complete plant, so you don't have to worry about your results. It can automatically reporting. If you are connects Excel sheets, so it will generate all the result in a Excel form. So you have to be very easy for that. And and the components are very useful to use, like just you have to drag and drop on the screen and it will automatically connect to the component. And visualization features I have told you, like graph, line graph, and other visualization techniques in this software you can use. And it has a designer feature also. If you want to use some design on your basis, on your sheet basis, like if you have some particular design for a component, that also you can use without affecting the other system. You can use the design, your design, in this system. Like if you see on the screen, this is the GUI of the Flownex. In the upper part, you can see the solve steady state, run, pause, designer, optimizer, sensitivity analysis. And if you see like run designer, it is showing. So like if you want to design this pump on your plant basis, like the flow rate and the RPM or head, so that also you can use the feature, designer feature. And like here, if you see on the bottoms, you are seeing that errors are coming. So here one by one you can eliminate the error also. Like if you model all the things and some inputs and some other part you given wrong, so it will show you here. So that also you can eliminate. And this is the input side for a particular component. So here you can give all inputs, and this is the component list. all the component I will show you in a software itself. This is just a picture of the main screen. So other tools has like Vidal said, means like if you want to connect with the other 3D softwares like ANSYS Structure, ANSYS Fluent, ANSYS CFX, OPC, AutoCAD. So you can link Flownex to these softwares if you want to perform some complex analysis or analysis that include both part 1D and 3D. So that also you can use in this. There is a link feature available in the Flownex, so you can connect all these things to the other 3D software and MathCAD, OPC, EES, and CCFX, and Fluent also. And if you have some different fluid that is not available in Flownex, so you can import that fluid from the DWSIM or NIST reference library. And so this is also a feature. And this are the list of Flownex users in India. IGCAR Indira Gandhi Atomic Research Center, BHEL Bangalore, ISC Bangalore, IIT Madras, Mumbai, Kharagpur, and BITS Pilani, Goa, Hyderabad, JNTU, Hyderabad, and CUK Gulbarga. Also, they are using Flownex software. And this is the all modules of the Flownex. Like if you want to purchase only thermal module, so it has a user basis choice. You can purchase only thermal module. If you want to use the electrical module, so you can purchase separately. So every model has a separate package. This software has. If you want to use advanced fluid thermal module only, and you don't want to use the electrical module, so you can separately purchase this version, so that you can easily use. So this is all about the software, just the introduction, and I will show you the just Flownex software GUI, and it has
So it is the Flownex GUI. Here you can see it is the project pane. Here you can the number of pages what you have added, that will be represented in this side. And it is your drawing plane. In drawing plane you can drag and drop component, and this component will be working. And here you can see these are the samples available for Flownex.
Just a second, sir. Just a second. For full screen option, you please manage your GUI. There is an option of hide everyone at the top. So there is an option of everyone, and when you click on everyone, there will be hide everyone option. So everyone will be hided, and all participants can see the full screen. So manage your GUI at your screen, because everything is the screen is visible for side. So please manage
No.
at your end. Okay, go ahead, Pratik sir, and please increase your volume bit. Okay.
Okay. Yeah.
Pratik sir, please mute everyone and then do the session. Okay, then resume the session. Please mute it, then resume.
Hello? Yes. Now my screen is visible.
Your
Yes.
screen is visible. There is no problem. Please mute everyone, because there is a lot of voices coming from other people. So mute everyone from your end.
Okay.
Because Dhananjay Wagolikar, someone is speaking.
Yes, it is the
So start now.
Yes, it is the representation of a small Rankine cycle. Uh, as you know, the Rankine cycle is two isothermal process and two adiabatic process, and that will be represented in this network. Here you can see there is a pump is there, and this pump is used to increase the pressure of the fluid, and gradually this fluid is heated, and after getting the heat it is expanded in the turbine, and after the turbine it goes to the reheater, and the reheater is modeled by the pipe element, and it again gains the heat and it expanded in the low pressure turbine. After that it goes to the condenser, and from condenser it again goes to the pump. So here you can see the TS diagram for this simple Rankine cycle. From this the pump is starting pumping the fluid, and at the point 2 it enters the boiler, which represents by this element, and by getting heat it gets turned into saturated liquid to saturated steam, and again it gets superheated, and this line is the expansion line from the turbine, which is isoentropic expansion from this point to this point, and after again it again gains heat from the reheater, and from point 6 to 7 it again gains the heat, and from point 7 it expanded in the LP turbines to the condenser pressure. So here you can see it is the expansion line from the LP turbines, and it is the entry point for the condenser, and from condenser at constant pressure the heat is rejected and it again goes to the inlet of the pump. So it is for the simple Rankine cycle. If you can add the regenerative Rankine cycle, it means multiple turbines will be there, and you have the feed water heaters and everything will be there. Then you can see we can also model that also. Yes, here you can see it is the Rankine cycle, which subcritical Rankine cycle, which consists of one HP heater and one LP heaters with one deaerator and boiler and condenser. So here you can see the process will be start from the boiler, which it's again gains the heat, and after gaining the heat it goes to the superheater, and here you can see this is an element where we are giving heat in order to getting the temperature of the peak temperature of 540 degrees Celsius. So from superheater it gains the heat, and it is the control mechanism. One control is known as PID. It means proportional, integral, and differential control, which calculates the error and putting the heat into this element. So this temperature will reach around 540 degrees Celsius. So from this you can see this line will represent the main steam line, and from this main steam line it goes to the turbine, and here you can see we can model the bypass line for that HP steam also, and from this turbine it again one line is goes for the extraction, HP extraction. Here you can see it is the extraction pressure. If we open the turbine element, you have the provision to provide the inlet pressure for the turbine, the inlet temperature, the design inlet temperature, and it is the pressure ratio within which the turbine will operate, and it is the design mass flow for which the turbine is designed. So for each and every plant, according to the flow rate, you have to change these design parameters so that the turbine will operate within the desired pressure limit. and this turbine is operated by Eclipse law. So in Eclipse law, basically it only calculates the pressure difference between these 2 points. It means the upstream and downstream pressure ratio, and according to that it will calculate the powers and the pressure drops. So here in this case you can see the turbine is producing 57.19 megawatt of power, and these two is actually the representation of high pressure turbine, and these individual components will represent the stage for the high pressure turbine, and the intermediate stage you can see we take an extraction for the HP heaters, and which HP heaters will be maintained at the pressure of 56 bar. So after that, this is the second stage of the HP turbine, and after expansion of the steam in the second stage, it goes to the cold reheat header, and this cold reheat header will also be connected with the bypass line, and from this header it goes to our reheater. For a regenerative cycle, reheater is important because you can see at the expansion of the HP turbines, the quality of the steam, which is 1.09, because it is almost going to saturate if any further temperature reduction will happen. That's why in order to improve the plant efficiency, we send that to the reheater. In the reheater, it again gain heat and increase its parameters. Like you can see the quality increase to 1.4. It means the heat content of the steam increase, which will derive more work from the turbine. And after the reheater, it goes to the intermediate pressure turbines. These three will be represent the intermediate pressure turbines, and individual turbine will represent the stages for the intermediate turbines. So you can see from the first stage, one extraction is taken out, and this extraction is going to the deaerator, which is maintained at 6 bar pressure. So the remaining steam will be expanded through these intermediate pressure turbines and goes to the low pressure turbines. In low pressure turbines, you can see the steam parameter is further reduced and the temperature is around 264.218 degrees Celsius, which was initially at 540 degrees Celsius. And after that, for a low, and there is one LP extraction is taken out between the intermediate stage of LP turbines, and it goes to the LP heaters. And after the last stage of the LP turbine, it goes to the condenser. So you can see from each turbine there is some power output is there. So if you make a summation of all the powers, so you can get the total plant power, which is producing now it's 289.0364 megawatt. So if you see the Rankine cycle, the TS diagram of this Rankine cycle, you can see it is a subcritical plant. It means the boiling process will be taking place at a constant temperature and constant pressure. So this line is represent the boiling, and from this point 14 it enters the boiler, and it 16 it exit the boiler, and this will be the superheater line. So you can see from this cycle, and the boiler is maintained at 163 bar pressure, and the saturation pressure is 348.86 degrees Celsius. So in order to model the boiler or any tank in which the phase change phenomenon is take place, so we use this component, and here you can specify the volume of the boiler, the connections. The connection means it is the outlet connection, it is the inlet connection, and here you can see the fractions. 0 means the bottom of the tank and 1 means the upper part of the tank. So this is the boiler outlet, and it goes to the superheater. And here this heat input is represented by this line. So from this line, here it expanded in the turbine. It is the first stage of the it is the uh, it is the first stage of the HP turbine, and it is the second stage of the HP turbine. So mm, so here this first stage line is this, and from 2 to 3 you can see it is the second stage expansion of the HP turbines. It is the second stage expansion of the HP line. So for this reheater, it is represented by the process 3 to 4 line. Again, it gains the heat, and at the 4 to 5, it again expanded in the IP turbines. So here you can see it is the expansion of the IP turbines. From 6 to 8, it is the expansion in the LP turbines. And at 8 stage, you can see from this graph, the steam is already saturated, so that the last stage of HP turbine undergoes is expanding the saturated steam. So you can see from this diagram also, at the downstream of the HP turbines, here the result menu, and the downstream of the HP turbines, you can see the quality of the steam. Quality means it is actually the mass fraction of the steam. So here you get the mass fraction of 0.94816, which is the saturated steam. So that has been represented in this graph. So in condenser, the saturated steam will enter. So the condensation process will be taking place inside the condenser, where the heat will be rejected to the any external medium. Maybe it is air, or maybe it is water. And since it is a constant pressure and constant temperature process, so here the heat rejection is taking place, and it reaches again the saturated liquid form. So here you can see from condenser the heat is rejected. It is the one heat transfer element is used. It is the element which can represent both the conduction and convection phenomena. So here you can see it is used to uh, make the heat transfer from the condenser to the atmosphere. So you can see from this element, you can specify the area for the conduction or area for the heat transfer. In case of our condenser, it will be the surface area of all the small pipes combined. And here you can specify the material properties for this condenser pipe elements. So individually you can specify this conductivity and capacitance, or you can specify any material from the database which is predefined. You can see here, you can see different types of materials so included inside the Flownex library. So here you can select any materials, carbon steel, chromium steel, anything you can also choose from here. And you can also specify the convection areas, convection coefficients, and your downstream convection areas. And you can also specify every heat transfer parameters within this element. So from this result, you can see from this cycle the total amount of 379.87 megawatt of remaining heat is transferred from the condenser to the atmosphere. So for that reason, and this process is happening at the constant temperature process, and from this the CP is there, the condensation extraction pump is there, which is one type of pump where you can specify the speed of the pump and the pump chart you can specify so that it will operate between two pressure limits. So this pump is extracting the remaining the liquids from the condenser to some specific pressure to develop specific pressure, and it is operating in 1500 rpm. And for any pump you can utilize this element, which is known as the variable speed pump. And here you can give the different types of pump curve. For this process I have used turbocharged pump variable temp cp. For this process I have used this pump curve for operation. So here you can see the maximum flow rate is maintained around 660 ton per hour. So, and the pump is operating at 1500 rpm. So from this you can see the volume flow rate will be around this much, 0.161 meter cube per second, which is the most efficient point for this curve. So you can specify the different types of curves, and which will be operate no, which is in between the pressure range and the volume flow. So you can also specify different unit of the pressure. So whatever pump curve you have, you can also copy from the Excel sheet and paste here, so that those values will directly come here, and there is no need to making that curve also. So here you can specify the curve. Here it is the efficiency. It is the efficiency curve for the pump, and here you can associate the operating fluid density. Suppose here you can see the fluid density in the condenser reaches around 63.77 kg per meter cube. So according to that, which curve you will be assigned, you can specify the fluid density here, so that the pump will work and operate to fluid that density of fluid. So the CP, this is the condensate regulating valve, which utilized to regulate the deaerator level. So the CP develops some pressure, and this is our condensate line, and here it is one simple model for the LP heaters, and it extends heat with the LP heaters, and from LP heaters it goes to the deaerator. Now, as I previously mentioned, from the second stage of the LP turbine, one extraction line is taken out, and that extraction line is goes to the LP heaters. The LP heaters is also a tank which deals with the phase change phenomenon of steam to water. So here you can see we specified the tank volume, the tank diameter, and the connection. As I said, the fraction or connection is the ratio of the top and the bottom. If it is specified as 1, then the line is connected from the top, and if it is 0, it is connected at the bottom. So here you can see at the it is since it is deal with saturated the saturation stage of the steam, you can see the mass fraction of the steam is 0.0039, and the tank pressure is 1.1 bar, and temperature is 102.29 degrees Celsius. And from this heat is taken out to the condensate line by this heat transfer element. Again, we specified all the areas, conduction elements and convection elements within these elements, and after getting the heat, it increases the condenser temperature. Here you can see the temperature, the discharge temperature of the CP is around 46.0942 degrees Celsius, and after gaining heat, you can see our temperature rises to 10136 degrees Celsius. So this elevated temperature fluid goes to the deaerator. In deaerator, you can see it is one extraction line is coming from the intermediate stage, and one line is coming from the HP turbine drains. So previously, whatever the condensate and the condensation happens in the HP heaters, this condensation will be directly transferred to the deaerator. From deaerator, you can see we specified also the same volume and diameter and the connection for the deaerator, and three lines are coming. The three inflows are happening to the deaerator. One is from the bleed, one is from the drain, and one is from the condensate. And from this deaerator, the BFP is connected with the deaerator in order to supply the feed water to the boiler. So yes, this pump is taking suction from the deaerator and pump the water to the um, boiler. So here we also specified the speed of the pump, and you can see we also assigned the curve for the BFP. You can see it is the curve of the BFP, and from this diagram you can see the BFP can rise a pressure around 180 bars, and it is the efficiency curve of the BFP. So BFP develops a pressure of 172 bar for our case, and this flow is maintained through this feed water line up to the boiler. So here it again extends heat with the HP heaters. You can see the HP heaters is also maintained at 56 bar and temperature of 271 degrees Celsius. So here it extends heat around of 41 megawatt of heat is extended from HP heaters, so that the temperature of the feed water increases from 162.62 degree to 205 degrees Celsius. And this feed water is again goes to our economizer, and economizer you can see we give the heat input so that the temperature of the fluid is all further increased up to 280 degrees Celsius, and this fluid is going to the boiler. In boiler we have to maintain the pressure around 163 bar, and it is that controller which maintains the pressure around 163 bar, and it gives the heat to the boiler which is around 131.134 megawatt. So that completes our this cycle. That completes our cycle. So if I run this model, you can see from the graphs the parameters are changing, and you can see the total turbine power output. Okay, okay. Okay. So, so it is the model for our subcritical power plant which operates below the critical point of water. So we can also model for the supercritical power plant. So here it is the model for the supercritical power plant. Here all the processes are same as for the subcritical power plant, and instead here we put the number of HP turbine, HP heaters, and number of LP heaters are there. Instead of one HP and LP heaters, we put three of them, and here you can see from the TS diagram that it is a supercritical cycle. It means the total saturation, the latent heat of heat gain is all eliminated here, and the steam is directly superheated and it directly goes to the turbine. So from this line you can see, if we run this cycle, you can see these parameters are changing and the cycle is operating at super in supercritical. And here you can see it is the flow network.
Participants, if you have any questions now, you can ask the questions at the end of the session, or you can just post your questions in the chat box. We will take at the end of session. Yes, Pratik sir, you can continue.
Yes.
Thank you.
So it is the heat balance diagram. For that cycle here you can see from the boiler it goes to the superheater, and from the superheater it goes to the HP turbines, and after superheater it maintains the pressure at around 260 bar and temperature of 593 degrees Celsius. Since the saturation and the critical point of water is around 223 bar, it is much higher than that, and for that reason we completely eliminate this latent heat of heat addition process, and it goes to the our HP turbines, and from HP turbines you can see those are the bypass lines, and this is the extraction lines which I have previously mentioned, and it goes, and again it goes to your cold reheat lines. And you can see from the this diagram, it is the extraction lines, it is the bypass lines, it is the reheater, and it goes to another extraction lines, and it goes to the IP turbines. And from IP turbine also there are several extractions are there, one for boiler, one for the D superheater, and this cycle continues, and it is just like the what I have previously mentioned, the subcritical power plant. So the total power output we are getting from this cycle is around 667.497 megawatt. So here you can see it is the total heat balance diagram where all the parameters are written. So it is the inlet for the LP, and it is the extraction parameters are there, and it is the condenser parameters, and it is the cooling water inlet and cooling water outlet. Those things are also present in this system. So it's all about the Rankine cycles. Now you can model the Briton cycles, the gas for the gas power plants in Flownex, for which you can see it is the model for the Briton cycle. And as you all you know, the Briton cycle operates between two adiabatic process. One is adiabatic compression, and then isobaric heat additions, and then adiabatic expansions, and then isobaric heat rejection. Here it is the simple one simplest
Pratik sir,
open Briton cycle. Yes.
hello, Pratik sir.
Yes. Yes.
Can
Hello.
you that notification sound? Because participants are saying that that notification sound is very disturbing for them. Can you please mute?
Yes. Yes, sir.
Okay.
तेरा वाला रेट सबके नहीं होता वो सेकेंडरी का जो रहता है ना सेकेंडरी का उसको बनाना पड़ता है देख उसको काटना रहता है इस टाइप से उसको पत्ती का
Okay. I think that notification sound is not from my end. Hello.
Sir, what is the actual problem? When the participants came in the go to
Yes.
meeting, that time sound came when someone enter in the meeting.
Okay. So is it possible to mute that audio from my side?
Yes, from your side.
From your side, sir.
And can you please mute all the other?
Okay.
Please mute yourself. If you are not able to do that, you can continue, sir.
Yes. Yes.
Okay, no problem.
Yes.
Dr. Khalid Nazar, sir, we will take question and answers in the end of the session. We will answer your all questions, sir. Please, Pratik, sir, you can.
Yes. So here is the representation of the Briton cycle, which is operate in open cycle modes. So it is not that it is not connected and it complete the cycle. It's only opens in open cycle. Uh, so for this Briton cycle, for the compression process, we used a compressor, and this compressor will take intake air from our atmosphere and compresses with certain pressure limit, and that pressure will be maintained in the combustion chamber. And for this compression process, we use this compressor, and we used the chart of this from. This compressor chart is used so that this compressor will operate according to this chart. And here in this chart you can specify the different parameters like the universal gas constant and the scaling factor, it means and the inertia for the compressor, and it is the vane angles. In vane angles it is mentioned 0 degree. You can add the different type of vane angles like 5 degree, -5 degree, anything according to the compressor design. And it is the corrected speed chart. As you know, the corrected speed is required because at each conditions, our atmospheric condition changes from the sea level. So in order to maintain a base, the compressor are designed according to the sea level, and according to our requirement, the corrected speed is introduced. It means it is the ratio of the actual speed of the compressor to the square root of the ratio of the temperature of sea level to the current atmospheric temperature. So this is important in order to maintain a uniform specification all around the world and all around the altitude to maintain the compressor. So here you can see there is also the corrected mass flow similar to the corrected speed. Corrected mass flow also the ratio of actual mass flow to the square root of the mass flow happening in sea level to the mass flow happening at operating level. And this corrected mass flow, and it is the pressure ratio. It means within this mass flow there is the curve is between the pressure ratio and the corrected mass flow, and we have to specify several lines for these mass corrected speeds. These are the constant speed lines, and for this each constant speed line we have to uh, input those corrected mass flow and pressure ratio values. For operating the compressor in Flownex, we have to only mention this upper line and lower line so that the Flownex will interpolate all the in-between points. And if you want for more accurate results, then you can specify number of graphs so that the interpolation will be accurate. So here the compressor efficiency chart. So from this chart, you can specify different efficiency. Similar to the pressure ratio chart, we have to only mention the first and the last pressure ratio lines so that all the points will be interpolated between these top and the bottom lines. So this compressor is here, and it takes the intake from the atmosphere, and the atmospheric pressure is 1 bar and temperature is 25 degrees Celsius, and the flow is maintained around 95.2 to 1 kg per second, and the compressor compresses the air, and the air reaches at the temperature of 496.644 degrees Celsius. And for this fuel we utilize the methane. You can see we utilize the methane gas for fuel, and the methane pressure is maintained at 22 bar and temperature at 25 degrees Celsius, and this methane is going to the mixing chamber, and from the mixing chamber it goes to the combustion chamber in which the combustion is taking place. And Flownex, there is one combustion option is there, the adiabatic flame. It calculates the oxidation reaction of methane with air, and the heat input is represent here, and it shows the temperature, and the combustion chamber is maintained at a pressure of 15 bar, and after that it goes to the turbine. The gas turbine operates between the pressure ratio of 15 bar to 3 bar. So since it is an open cycle, it directly goes to the atmospheric. If we add any combined cycle arrangement will be there, then this parameters, so which is around 300 kilopascal and 1596.780 degrees Celsius, is quite enough to convert the water to steam. So this parameter can directly goes to the combined cycle. So since it is open cycle, it is goes to the atmosphere. So this turbine is operate between the pressure ratios 15 bar to 3 bar, and developing the pressure, developing the power of 96.277 megawatt. So here it is the TS diagram for the Briton cycle. So here it is, since it is not a perfect adiabatic process in the compressor, the line deviates from the straight line, and the compression exits at this point, and here the heat addition is taking place in the combustor, and it is the turbine inlet, and from turbine inlet it goes to the exit of the turbine, and it expanded and produces the uh, power. So here you can see, if I put the straight line, it also deviates slightly from the straight line, because we give the turbine the isoentropic efficiency of 0.915. That's why this line deviates from the isoentropic line, and it is the TS diagram for the Briton cycle. So if I run this cycle, you can see, and now what I'm going to do is change the inlet temperature. Suppose in our winter the temperature remains around 25 degrees Celsius, and summer the temperature rises 10 degree or 15 degree. So that also affect the power output and the pressure and the performance of the cycle. So you can see now I'm going to change this temperature from 25 degrees Celsius to 45 degrees Celsius, and see the effect, whatever effect it might have on the system. So you can see there is the temperature is now rising, and if you see the graph, you can see the turbine inlet temperature is increasing as the inlet temperature of the compressor also increasing, and it is the turbine outlet temperature, the curve, and it is the compressor outlet temperature, it also increasing as the atmospheric temperature increase. So it is the combustion chamber pressure, since the temperature of inlet air is increased, so that it increased the combustion chamber temperature. So from the previous value of 15 bar, now it reaches to 15.22 bar, and similarly it also affect the total power output for the turbine and the total power intake for the compressor. So this blue line represent the turbine power output, and the red line represent the power consumption for the compressor. So you can see as the air density of outside reduces, so initially the compressor was taking 54 megawatt of power, and since the density reduces, compressor did more work upon the air, so the power demand for the compressor also increased from 54 to 61. So there is around 6-7 megawatt of power gain from the compressor. So here you can see the temperature and the temperature uh, for the turbine inlet and the combustion chamber. So you similarly in a different type of scenario you can create and you can model in Flownex. It might be a complete Briton cycle or a open cycle or a combined cycle, and you can, by changing the parameters, you can see those effects, whatever effects it have on the system, and according to that you are going to change the design and optimize the design. So for this case, I have only increased the temperature, so it has these effects on the process. So here you can see. Similarly, you can model different type of other cycles like
कठिनाई होने पर तुरंत राज्य हेल्पलाइन या राष्ट्रीय हेल्पलाइन नंबर 1075 पर संपर्क करें। भारत सरकार द्वारा जनहित में जारी। नमस्कार, आपण ज्या व्यक्तीस कॉल
yes. So we also developed another cycle for the cogeneration plant. It is a geothermal cycle. In
Just wait a
this
second. Participant, please be in the session only. We will share the feedback link in the chat box only. It will not be shared in the WhatsApp or Telegram group. So if you miss the feedback link in the chat box, we will not share that to you personally. So be attentive in the session and please be live in the session. If you and we'll announce when we'll share the feedback link. So be attentive, be live in the session. Don't leave the meeting in the middle. Okay. So soon we are going to share the feedback link also and in the chat box. Okay. So please be attentive in the session. Don't leave the meeting.
Yes, continue, Pratik.
yes. So it is a model network for the geothermal cycle. In geothermal cycle, the heat input is getting from the geothermal heat, and this heated parameters is directly goes to the turbine and it produces the heat. So there is no need for external heat input medium like coal or gas is there. So from this geothermal temperature we are getting the steam, and we utilize that steam for power generation or any process work as well. So here you can see it is the water supply from the geothermal wells. You see the pressure is around 600 kilopascal and temperature 200 degrees Celsius, and have in somewhat superheat region. So this steam goes to in this line, and this element is the steam trapper. The work from this element is it separate the saturated steam or the saturated phase of liquid, and only steam is allowed to pass through. So you see the previous flow is 29.23 kg per second, and after the separator, since it is already in superheat region, so there is no need to separate the steam, and it goes to continue in this line. Here you can see there are small two cycles is there. Actually it is the Hexane cycle. It means another liquid is utilized. It is also a Rankine cycle, but instead of getting heat from coal or gas, it exchange heat with this steam line, and after getting the heat, and it expanded in the turbine so that the turbine produces the heat, and that hexane is condense in this heat exchanger with exchanging heat with the atmospheric node. So there are two Hexane cycle at there. One is producing 6.604 megawatt of energy, another producing 3.68 megawatt of energy. And you can see after 8 exchanger of heat with exchange in Hexane cycle, the quality of the steam reduces. Here you can see the quality is 1.04 and temperature 200 degrees Celsius. After fast heat exchange, it reduces to 0.78. It means the dryness fraction reduces and some liquid came to the steam and it becomes the steam water mixture. So here it again exchange heat with the second Hexane cycle, and again the steam quality reduces to 0.627 and the temperature also reduces. Since we are supposed to connect one steam turbine in front of this line, and the saturation and it is already in the saturated stage of steam, so we have to remove those liquid particles from the steam. So that's why we use this steam trapper. It means it separate the liquid phase from the steam phase, only and only steam is allowed. So here you can see the total mixture is coming 29.23 kg, and after that 18.2893 kg is only passed. So you see here the quality again changes to 1.01 and previously it was 0.627. It means steam trapper extract all the fluids from this line and only steam is allowed, and that steam is expanded in this uh, turbine. So this turbine produces the power of 4.261 megawatt. So the total cycle production will be this power plus this power and this power. And after expansion of this, it again exchange heat with another water source. So it maintains the water supply line at a temperature of 55 degrees Celsius, and the remaining water injected into the well. So it is the diagram, it is the network for the uh, combined cycle, geothermal combined cycle, and it is the line diagram. You can see all the parameters are written here, and it is the first heat exchange process, it is the second heat exchange process. After that it is the steam trapper, and it changes it separates the water phase, and this water phase is injected to the water well, and the steam, only steam is expanded in the turbine, and this turbine also exchange heat with this water supply, and again all the waters are going to the injector well, and the heated water goes to the warm water supply. So here the Hexane cycle, in Hexane cycle we use the pump which maintains the flow of 75.62 kg and 42.516 kg respectively, and this is the same Rankine cycle as steam, but instead of water we use the Hexane, because Hexane has low boiling temperature as compared to water, and it expands in the turbine and produces the power, and those remaining heat is rejected to the atmosphere. So if we okay, it is for the geothermal energy cycle. Now in Flownex you can also model other cycle like solar Rankine cycle like this. It is the model for the solar Rankine cycle. It means the heated medium is mm, the solar collectors, and from the solar collectors it gains the heat, and this heat is exchanged with the steam generator just like our normal Rankine cycle, but the heat exchange medium is different. Instead of coal and any conventional medium we use the solar power. So here this solar line exchange heat with the steam generator, and these two components are insulated pipe. You can specify the insulation so that the heat to minimize the heat transfer between the pipe and the surroundings. And from this cycle it is the steam generator gains the heat from this cycle and again it expanded in the steam turbine, and from the steam turbine it goes to the air cooled condenser. It means it exchange heat with the atmosphere. Here you can see the total amount of heat rejection is 10 megawatt, and the total amount of heat input is uh, 17 megawatt. And the steam turbine operates um, and the steam turbine operates at 3000 rpm, and for this turbine you can also specify the turbine curves. You can see this it is the turbine curve in which this steam turbine operates. Similar to the compressor, the steam turbines also we have to specify the different type of corrected speeds and the pressure ratio, mass flows, and gas content. And from the result window you can see the total amount of power produced by the steam turbine is 3.05 megawatt, and the total torque produced which will subsequently utilize for rotating the generator is 9717.39 newton meter. So similarly, if you can see the effect of temperature and pressure change or any effect on the cycle, you can also see those things. For example, now I'm going to change the temperature for this primary loop cycle, and what effect it will bring on the total entire cycle. So here you can see I'm running the cycle. Here you can see the steam generator level is changes, and the level is dropping down because the amount of heat exchange with the primary cycle reduces. Since the temperature increases, the pressure also increases inside the steam generator, and since the pressure increases, you can see this pressure, the steam generator level also decreases. So you can see the change in turbine power. As the temperature increases, there is a little dip in the turbine power, and it is the pressure for the steam generator pressure. As I have mentioned, the pressure is starting to decrease. Pressure is starting to decrease, and it is the condenser pressure. And after increasing at certain level, the pressure is maintained. So it is the turbine quality, and it is the TS diagram for the Rankine cycle. Since there is no superheater is there, uh, so there is no peak in temperature. So only we can see there are two constant temperature and pressure lines here there, and it is the expansion in the turbine, it is the exit of the condenser, it is the entry of the boiler, and it's complete our solar Rankine cycle. So we can also model a complete water Rankine HPD complete turbine Briton Cycle. Good. So
Sir, in the meantime, please see the chat box. There are some questions. Okay.
yes. Okay. So okay, this refrigeration cycle will be the last cycle which I am going to explain. Then we can start our question answer session after that. Okay. Okay, this is the cycle for the reverse Briton cycle or the refrigeration cycle, or this a vapor compression cycle in which we use the fluid R22 as vapor, and it is the working fluid which operates within the cycle, and Here you can see these are the components utilized in the cycle. The first component in the Briton cycle, in the reverse Briton cycle, is the compressor, in which the R22 is compressed, and after compression it gains some heat. So here you can see it is the element of positive displacement compressor. It also present in the Flownex library. In Flownex library you can also see the positive displacement compressor is there. Here you have to specify the speed of the compressor, and it is the swept volume of the compressor, and it is the dead to swept volume ratio. It means there might be some gap between the top dead center of the compressor to the wall, and that will be the dead volume, and you have to define the ratio of dead to swept volume. And this ratio is important because it is utilized to calculate the pressure ratio and efficiency of the compressor. So here you specified the isoentropic efficiency for the compressor is 0.9, and this compressor compresses the R22 to a pressure of 505 kilopascal, and to the pressure of 1958.4 kilopascal and temperature of 84 degrees Celsius. And it is the heat exchanger, in which we have to remove the heat from the R22 fluid, so that it is going to expand in the expansion valve, and in the reduce expansion valve, and it reduces its temperature by losing the enthalpy. So here you can see it exchange heat with an external media, where it rejects the heat, so that the temperature is dropped from 84.64 degrees Celsius to 50 degrees Celsius, and it goes to this pipe, and this is the expansion valve. In this expansion valve, we have to specify the diameter of the valve and the discharge coefficient, and discharge coefficient is important for isoenthalpic expansion process. So the temperature will reduce, and here you can see the temperature reduced to 0.7205 degrees Celsius. So from the temperature of 46.8 degree to it reduces to 0.72 degrees Celsius, and it is our required cooling medium. Whatever we want to cool, you can put that into this medium. So it exchanges heat, and it reduces the temperature of the cooling fluid to 7.7214 degrees Celsius, and after that the R22 gains heat from the cooling medium, and it again goes to the inlet of the compressor. So this is the cycle. If I run the transient scenario for this cycle, it means some temperature parameters and some pressure parameter will change. That will be reflected on the system. So Flownex has the capability to show the changes with the system, and we can rectify those changes according to our design specification or our need. So here you can see, and the total mass flow and everything is changing. We are now changing this diameter. So this flow is also changing. This temperature is also changing. Due to that have the effect on the coefficient of performance of this cycle. So you can predict those type of scenarios within Flownex, in which you can model different type of systems, subsystems, cycles, and sub-cycles. Everything you can model, and you can optimize, rectify your networks by utilizing this tool. And now if you have any questions, you can ask me.
Pratik sir, in the chat box already there are some questions. Please start from the beginning in the chat box. Go to the chat box sections and see that.
Participants, also you can post your questions in the chat box, or you can unmute yourself and ask us a question.
Yes, you can, by unmuting yourself also you can ask, and as well as you can post in the chat box. Pratik sir, can you see chat box?
Hello, sir.
Yes, please go ahead.
Yes, hello.
Is
Hello.
there any provision to design the whole dam system right from dam to up to the powerhouse?
It means you are talking about the hydropower plant.
Hydroelectric power station.
Yes, now it is not the provision in this, but you can do that. There is another method. Here you can see. Let me show you. Here you can see one element is there, script. It means it is written in the C# language. So you can specify, but you have to need some programming skill. You can put your own formula, and so that you can calculate those your hydro turbine parameters within this environment. So it is possible, but now in the stage there is no such components in which you can simulate the hydroelectric power plant.
Yeah, basically,
Okay,
sir,
thank you,
this
sir.
is basically designed thermally design cycles.
Yes.
But direct
Okay.
provision for cycle is not there. So indirect way you can write down your formulas and then you can do the calculation accordingly.
Yes.
Okay. Sir, is there any provision
Hello.
that we can import direct the formulas? Formula list is available?
No, there is no such provision. You can write your formulas within this environment. It is not that you can export
Okay, sir.
directly, but you have to write.
Okay, thank you.
Okay.
Hello.
Next question. Next
Yes,
question.
yes.
Hello,
Yes, please.
Pratik ji.
Please go ahead.
Pratik
Yes.
ji,
Yes.
I have one question.
Okay, sir.
In the last slide, you have shown that the vapor compression cycle to
Yes.
the reverse Briton cycle. How it is
Yes.
possible? Reverse Briton cycle is same as the vapor compression cycle. You can't say. Never say. It's a different one.
No.
Reverse,
Yeah.
totally different, because in the reverse Briton cycle, you have used the turbine to expand the air. That is for the refrigeration air cycle. But when you
Yes.
go for refrigerant, you have to use the
Yes.
vapor
Yes.
compression
Yes, sir.
cycle. That's
Yes, sir. Yes, sir. I get it. Yes, sir. I get
you
it.
are
My
last
mistake.
slide
My
you
mistake.
told. I think
Yes,
that
sir.
is
I get
not
it.
the truth.
Yes. Yes, sir. Yes, sir. That is
And,
open air
and
cycle. Okay.
yes, that is for the air refrigeration
Yes.
cycle,
That is
not
air
for
refrigeration.
the vapor compression cycle.
Yes. Yes.
Secondly, one that you have told in the previous slide that the dryness friction is 1.04 and 1.01. That
No,
can't
no.
be possible because
Yes,
it's a
that is.
maximum.
Yes, sir. That is not possible. The dryness fraction will remain only between 0 to 1. But
One definitely maximum
yes,
more than even theoretically or practically.
yes, sir.
It's
Let me
not more
explain.
than one.
No, no, no. I am not telling about that. Let me explain. Here in Flownex tool, there is one parameter is called quality. You can see uh, when I click in each node, it is the quality. So this quality is equal to dryness fraction, but uh, it only operates between 0 to 1. So suppose if anything happens above the saturation temperature and pressure, so it shows the quality is 1.024 or anything greater than 1. It is actually not a dryness fraction. It is only the quality represented
That's a
in this
quality.
software.
You are already
Yes,
saying quality means dryness friction. Nothing else.
yes,
If you are talking
yes,
about the quality, that is the dryness friction. Nothing else.
yes. I am only
It means
talking about dryness fraction below when it is below 1, not about
definitely. But
more than 1. Because that
whenever you go after the saturation, your enthalpy level will increase. The total energy
yes,
content will be increased. That's a
yes, yes,
but you can't say it's 0.4 because it's totally different. Because it will limit the fundamental.
yes. Actually, it is not. It is one parameter is quality. It is only showing that whether it is
One
superheated or not. There is no relation between the dryness fraction. Only when the quality is in between 0 to 1, then you
even
can relate it between the
even
dryness fraction.
whatever you tell, if you are telling you choosing the word quality or dryness friction, it should not be more than one. It will create some misunderstanding for the listeners.
Yes. Okay, sir. I'll take care
Second
of
more
that.
thing that I want to ask you, take some problem with the evacuated tube collector, flat plate collector, solar distillation system, solar water heater system. even solar power plant real, which is there in Maharashtra. There is, I think, 2 or 3 power plants nearer to the border of Gujarat and Maharashtra. You can take the problem of this. So it will be better to understand if we will go to the real problem, because we know how the condenser work, what will happen, why we are connected. These we all know.
Yes,
But
sir.
changing the value and changing the diagram, changing the design, how it will give effect? Means if I have to go beyond the efficiency more than 30%, what type of the setup we should have? Where we can change?
Yes, sir.
Where we can get the energy?
Yes, sir, that will be
That type
possible,
of problem we
but
have to take. Yeah.
yes, sir, that will be possible in this software, and we
And
are also
how?
doing that process.
Yes. About it,
One more
it's
thing.
very
That how we can use your software for the research purpose. How it will be helpful.
Yes.
How it will be helpful for research purpose, sir?
Yes, for the research purpose, you can optimize and predict the parameters. Here there are some tools are there, like optimizer and sensitive analysis are there. So in these tools, you can put the
which
design
software is used here.
If there
here.
is some open software is available, online software available, just share the link to me. I will go on that and try to solve some problems, if possible.
Yes, actually, whatever you said regarding the complete plant thing, from complete plant, we need actually the control to model the total plant. So in general, by getting the
Then
data from the direct
the complete
plant,
plant. I'm just telling some small problem. We can share we can distribute the problem to the student, and then we will tell them to answer to the software. Some
yes,
small problems, small changes. If a group come to me, and I give them the problem. You change this parameter. Another group, I told them that change this parameter
yes,
and
yes,
see
yes,
the efficiency.
yes, sir.
Yes,
That is
yes,
definitely
yes,
possible.
sir.
Good afternoon. Can I ask something?
Yes, sir. You can
Yeah,
ask.
Mr. Pratik Kumar, thanks for the nice presentation. I am Dhananjay Vagolikar from Pune. I have a couple of requests. First one is, can this presentation be made available for later study also? This is first request. Secondly, I just want to know in what way this particular presentation or this Flownex can be linked to CFD related analysis for thermohydraulic flow analysis.
Yes, sir.
Thermohydraulic analysis, like say in solar systems, solar air heaters or solar dryers, or conventional electrical dryers or fuel fire dryers, or even water heater type of things. So, in what way this database or this platform can be used for thermohydraulic performance analysis under CFD vertical or electric? Can there be any link available? So these are the two
Yes.
requests I have.
Here you
Yes,
can
sir,
see.
it will be available.
Hello.
Sorry. Hello.
Hello. You can see in the screen there some API arrangement is there. Here you can see you can link this with ANSYS and link with MATLAB. And in ANSYS workbench, you can also predict the 3D parameter changes and import those results to Flownex. So Flownex can work with other tools, but you have to make some API which will be interact between these two interface between them. So it is possible, but you have to make some in between interface for them.
Acha. Couple of things. Is any truncated version, if at all, if this full version is available free, that will be really very great, and thanks for that. But in case it is not possible to make it available in public domain as a free,
Dhananjay sir, full version is not available. Okay, at free. Okay, you have to purchase, sir.
any truncated version is available, some with some limitations. Is it
No,
available
sir,
free
no,
for
because it's
demonstration?
a industry standard tool. No, sir, it's not actually demoli available for 15 days or 1 month. Okay.
Okay. Demo it is not available.
No, no, sir, no.
Okay, thank you, sir. Thank you.
Hmm.
If anybody wants to ask questions, please go ahead again.
Participants, as we know, the pandemic is going on, so we are actually providing the Flownex cloud-based license. Okay, those who are interested to work remotely. Okay, so we are also providing the cloud-based licenses. Those who are interested, please mail me on my mail ID. I have mentioned my mail ID in the chat box, which is shiv@indiasoft.co.in.
Feedback link is shared in the chat box. So please see the feedback link. In the meanwhile, those who want to ask question, please go ahead.
Is there any other questions, or we can put in the?
Participants, please unmute yourself and ask questions if you have any questions.
Sir, I am not able. Thanks for the presentation and arrangement, arranging this Flownex presentation. Thank you, sir.
Thank you, sir. Thank you, Dhananjay, sir. Participants, please unmute yourself and ask questions if you have. Yes, sir.
Sir, where is the feedback link?
Sir, it is mentioned in the chat box. Please check the chat box. It is already mentioned, sir. Participants, you can unmute yourself and ask questions in the.
Hello, sir.
And by you can ask even questions by the even chat box also.
Hello, sir. Sir.
Yes.
Yes,
Yes.
Sir, good afternoon, sir. Very good presentation given by the resource person. And my doubt is that based on this Flownex software, is there any paper published by using this Flownex software?
Yes, there are several papers are available in the Flownex for which.
Please show paper, sir, if you have in the library with you.
Yes. So if you can share your contact with us, we can provide you some papers regarding the Flownex. Actually, it is not publicly available. Those papers are available for the channel partners. So papers are there. So if you can ask and share your contact, we can provide you that.
Yeah, definitely, sir. I will share my mail.
Sir, I have mentioned my mail ID. You can mail me for those papers. We will give it to you then. Okay.
Sure, sir. Sure, sir. Definitely, I will contact you.
Okay.
Sir. Thank you.
Any other queries? Any questions? Please ask us. Please unmute yourself and ask the questions.
Feedback link is available in the chat box. So please fill the feedback immediately.
Participants, any questions?
Yes.
On Flownex? We are actually giving the two type of licenses. One is academic and one is research. Okay, those who want to publish the papers and do the research work, they go for the research licenses.
Hello.
Yes.
Yes.
Hello.
हाँ सुनील जी, it's Ajay Tripathi here.
Yes, sir.
ये बताइए, हाँ ये बताइए, there are already so many simulators available with all the top power plants. Like if you talk about NTPC or any, they are having their own simulator. And and the हाँ नमस्ते, कैसे हैं आप?
अरे बढ़िया है सर, कैसा लगा सॉफ्टवेयर?
अरे बढ़िया, वही तो मैं इसीलिए पूछ रहा हूँ कि मैं
ठीक है जो अपन जो हाँ बोलो।
मेरा जो
बोलो, बोलो।
जेपी में मैं था, जेपी में खुद का इनका पावर प्लांट का सिमुलेटर था। तो यदि मैं उससे यदि आपका कंपेयर करूं तो वो तो बहुत हाई फाई करोड़ों में उनका सॉफ्टवेयर था। और तो इंडस्ट्री में सबके पास अपने पावर प्लांट सिमुलेटर है, तो उसमें आप इंडस्ट्री में कैसे यूज आता है आपका?
You can use
अभी
this software.
इंडस्ट्री का नहीं, ये अपना हाँ, this is useful for your students. Industry and corporate people, how they are using, we will send you separate guidelines for that.
Okay.
No, sir. Actually, different types of industry are also using this software. You can see IGCAR is also using this Flownex. BHL also using this Flownex. Different type of IITs
So
also
these
using
case studies we may share later with you, sir.
Yes, you can share.
Yes. Now you see the academic benefit. Industrial benefit we will come to you later on a bigger scale.
फ्लोनेक्स भी आपका प्रोप्राइटरी आइटम है कि नहीं?
ये प्रोप्राइटरी आइटम है सर, ये डायरेक्ट कॉन्ट्रैक्ट में निकल जाएगा।
अच्छा, ठीक।
Don't worry, we have the sample orders and all those things. जैसा अपना रेगुलर रूटीन है उसमें नोट शीट में बन के चले जाएगा वो।
ठीक। ओके।
I'll give you the next guidelines. खाली सॉफ्टवेयर पे आप फिदा हो ना?
ठीक।
हाँ बस, ओके।
Thank you.
Okay, next questions.
Hello.
Yes. Hello.
Yes, I have one question. You have mentioned about the cloud-based link. So that is also charged one, or is it for demonstration? Because what is my observation is the academician also requires some good hands-on practice. So the teacher
yes, sir, we will
has some practice.
Chargeful, sir.
Because the institutions will not directly. Sorry.
Sir, after the purchase of the software, now we will give you full-fledged training, sir, on Flownex.
Okay.
Online or
offline? Okay, because in present COVID situation, most of the educational institutions, they are functioning, including ourselves, online. So in that, its utility for that needs a personal exposure and training and hands-on practice by the user first. That is what is my opinion.
Yes, sir. We will provide you on online basis. So don't worry about it.
Okay. And one question about this feedback link you have given. In that it is asking for experience. Yes. So if it is industry and teaching, it asks for must be a member. So member what, sir?
Which member?
Your experience in years, industry plus teaching. So mine is 10 years industry and 17 teaching. So I am finding it difficult to fill that field, and it says it is compulsory.
Okay. You can mention your teaching experience, sir. No problem.
अच्छा, sir. Okay. उसके बाद भी must be a member है, देखता हूँ. Fine, I can deal with it.
Any other questions? Any other questions from the participant?
And one more is a small doubt was there the fuel in gas turbine plant cycles which you have explained. The fuel is methane. So is it only for methane, or we can have different varieties of fuels, like combination of that, because natural gas is normally used. So it is a different alkanes and.
Yes,
Okay.
yes, you can use different
that,
combination of gases. You can see my screen now.
Yes, yes.
Yes, here there is an option is called the mixed fluid option is there. You can
Acha,
get
yeah.
different types of fluid. Here, suppose
Okay.
I click on this, you can see a lot of fluids will be coming. Here you can see
Acha.
air, isobutane, propane. So anything you want to mix, you can add in this pane, and so
Acha.
that according to that, the mixer fluid will continue to work.
Okay. And there is no provision of the closed cycle gas turbine is not there. It's either
Yes,
open
yes.
or
No, no,
combined
no.
cycle.
You can make that closed cycle, but actually we don't have any design regarding the recuperator in which we can get the heat back. So that's why it is not model in this network. So it can be
Okay.
model. All flow related, almost all flow related models can be made within this software.
Okay. All right. Thank you, Mr. Pratik. Thank you, Mr. Shiv.
Thank you, sir. Thank you. Thank you, Parag, sir.
Thank you.
Any other questions from the other participants? Please unmute yourself and ask, or otherwise you place your questions in the chat box. If you are interested in the cloud licenses part, please mail me on shiv@indiasoft.co.in. Those cloud licenses, after 1 year, it will be converted into the network licenses. And these are perpetual licenses. So if there is no questions, then we can conclude the session. I would like to thank all the participants for joining, and especially mainly thank you to the Pratik sir who have given us the time for the presentation. Thank you, Pratik sir, for your excellent presentation.
Yes,
Okay,
thank
so
you,
we are
sir.
concluding this session, and the more session updates will be given to you on that Telegram group as well as on the WhatsApp group also. Okay, so there will be more program on Flownex from our side. So please stay tuned. Thank you so much, everyone. Please, thank you.
Okay.
There is a
Thank
feedback
you.
link is mentioned in the chat box. Still, if anyone have the questions, they can ask or put your questions in the chat box also.
So participant, please submit your feedback by the evening. And after evening, the link will be closed. So today only you have to submit the feedback.
Is there any questions still from participants? Because we are going to conclude the session within next 2 minutes. If anyone have, please ask. Okay, so we are concluding the session. Thank you, everyone. Thank you.
Okay.